What you have, of course, in organic molecules, biological molecules, you have more extended conjugation systems. You have aromatic rings and double bonds and so forth. So you need to have some idea of how that affects the position of these bands. So the simplest one you can look at is you can look at your acetone again. We know the lambda max is at 187 and 270 nanometers. We've assigned these to this is to the end, to pi star, and then the higher energy one, the lower wavelength one, is assigned to pi star, and there's a difference in intensity. And what you find for this one, though, which is a very similar molecule, this is metal vital quinone, you just added another CH2 here. And when you look at the UV visible spectrum of this, you find that these two bands again occur, but now they've moved to higher wavelength or lower energy. So what the reason for this is that when you have a pi bond here in the carbonyl and you have a pi bond here. So the pi orbitals aren't just composed of this C double bond O component for this. You get some mixing into the pi orbitals of this CH2 group as well. So what you have, what you call your extended conjugation. And when you get a more extensive pi system of conjugate double bonds, what you find is both the inter-pi star and the pi to pi star transitions occur at a longer wavelength. And what's basically happening is you have a decrease in the energy gap. So the more extended the system, the electron spreads out more, and what mainly happens is the energy of the pi star orbital comes down quite a bit. So you have represented here. Here you have without conjugation, and here you have it. Here you have it with conjugation, and now the gap here is smaller. So if the gap is smaller, the pi star has come down, then the this is the pi to pi star transition. That will occur at a lower energy and occur at a longer wavelength. And also the same, of course, occurs for the end to pi star, because the pi star has come down, so the end is, say, somewhere here. So now this gap has dropped as well. So what the effect of conjugation usually is to increase the wavelength of the UV visible band. Right, so again, summarizing what I just said for your notes is that the conjugation decreases the energy gap between the HOMO and LUMO, and therefore you need less energy for electronic transitions. So if you have less energy, it means the UV bands occur at longer wavelengths. And then you have example, if you have, sorry, if a compound has enough double bonds, it'll absorb visible light in the visible region. So if we look back at these transitions here, we're talking about 187 to 270 nanometers. Now acetone is colorless because it's got no transitions in the visible. The visible region goes from about 400 up to 700. So these all lie in the UV region. So you don't get any absorption from the visible spectrum, so it's colorless. Likewise for this compound here, I've never seen it, but it's going to be colorless as well, because these transitions 219 and 324 nanometers, they're in the UV region. So you're not taking any, abstracting any colors from the visible spectrum, so it's going to be a colorless. But as we mentioned here, as you go up and get further along, say you had the simplest one would be etene, and then you might have conjugated systems like that, and you can actually show it with these different forms of double bonds, that as you increase the number of double bonds, you start to push this band, UV visible band, higher and higher wavelengths. And basically what you're doing is you're pushing it towards the visible region of the spectrum. And the best example of this then is beta carotene, which is present in carrots, and you all know that's what gives a color to carrots. or tomatoes as well, apparently. And what that is then, well, I think we have a picture of it here. Yeah. So here you have beta carotene. I've got a few groups on the end, but what you can see here is it's mainly got a lot of double bonds, bond conjugation. So here we've increased the conjugation up, so we decreased that gap between the pi. There's a pi and pi star transition here. You've decreased that gap quite a lot. So now you've pushed it up to 455 nanometers. So 455 nanometers, of course, is just here in the spectrum here. You show the UV visible spectrum for beta carotene, and you can see that its main band here is, well, it occurs about 455, but then if you impose the spectrum, the visible spectrum, on it, you can see that it's absorbing here in the blue and the green region. So the idea of a color of something is that you're absorbing in the blue-green region, so that's absorbed, and the light that comes out, which you see, is going to be the red-yellow. Okay, so that gives then you the color for the beta carotene. Okay. Right. So you've got a lot of this type of system in biological systems, and perhaps the best example is chlorophyll A, which occurs, as you all know, in green plants. And of course, if you do the absorption spectrum of chlorophyll A, you get two bands in the visible region. And of course, the reason is here it's not. We talked about beta carotene. It was a linear system, but chlorophyll A is a ring system, but it's just got rings of double. These are all alternating double bonds. So it's got a conjugated ring system of double bonds, and therefore you get pi star transitions. And because it's a conjugated system, the pi to pi star transitions occur in the visible region of the spectrum. And here in chlorophyll A, you get two bands in the visible region of the spectrum. And here what we've done is we superimpose the spectrum onto it again. The visible spectrum is composed of the colors of the spectrum. So you can see that one band here absorbs strongly in the blue region of the spectrum, and you have another band here that absorbs in the red region of the spectrum. So what's left when these are absorbed is the green region of the